Hi, welcome to a new session of electrical machines. In today's class 4 under single phase transformer on load, we are going to see the actual phasor diagrams with primary and secondary windings. In our past classes of electrical machines under transformer, you can go and listen to class 1, 2 and 3 for which I have provided the link in the description box. You can check those videos and you can come back to this video. So we'll start off with this actual transformer. So what we know that when an input single phase AC input is applied to a single phase transformer due to mutual inductance, the flux sets up in the secondary winding due to primary winding, which is supplied by input voltage source V1, which is delivering a current I0, which is known as a no load current when the transformer is not loaded. Then we have also seen in our past classes about the EMF equation of transformer E1 and E2, which are obtained in primary and secondary windings. Then we have shifted our attention to the transformer on load conditions. Means what? The secondary is connected to a load and the voltage is measured as a terminal voltage across the load. So for drawing the phasor diagrams for different sorts of loads, that is resistive load, inductive load or capacitive load, what are the assumptions we made? So we consider here without primary winding and secondary winding resistance and reactance, V2 is equal to E2 and V1 is equal to minus E1. And the secondary current is in phase, lags behind and leads the secondary voltage V2 across the output terminal voltage by an angle phi 2 for a pure resistor, inductive or capacitive loads respectively. This is what we have seen in our past class. And we have also seen the phasor representation under resistive load. You can see a flux diagram and E2 is equal to V2, V1 is equal to minus E1 and I2 is in phase with V2. Then to find out the primary current, we have the no load current and we have the load component of the primary current. Then combination of these two gives you the primary current, and the angle phi naught phi 1 is obtained per a unity power factor for a resistive load when it is connected as a load for transformer without resistance and reactance components on the primary and secondary winding. Similarly, we have seen for the inductive loads how the phasor diagram is changed, where you can see I2 is lagging V2 by angle phi 2 and the respectively the power factor angles are made with respect to the uh, no load current and load component of the primary current. So this is how it is observed in the case of inductor. And the case of capacitor, again we can see the current here, it is leading voltage by an angle phi 2, and again when the primary current is taken as a phasor sum, it is obtained in this fashion. And what is the conclusion we have made from this? That for a single phase transformer on load, these are the phasor representation diagrams. Now what happens if we have the windings which is composing of the resistive and reactive components in the primary and secondary? To understand this, I can show you the equivalent circuit of actual single phase transformer. You can see this is the core of the transformer where we have a primary winding. Here you can see you have a resistor and inductor shown in the primary winding, and we have the supply input voltage V1 which is supplying the current in N1 turns as I1, and E1 is the induced voltage which is known as the self-induced voltage of the primary winding, and R1 and X1 are treated as the real component and the reactive component. Overall this is treated as the impedance of the primary winding, and the drop when current flows through resistor is I1 R1 and the drop across reactance it is I1 X1. So this primary induced voltage sets up the flux which links the secondary of the coil also, and when the secondary is connected to a resistor and reactive component in the secondary winding, uh, the winding is treated as here as N2, and the developed voltage due to phi will be E2. Then the resistor and the reactive components of the impedance are treated by Z2, and when the load is connected, the current starts flowing, and that current is here treated as I2. And this current, when it travels across the resistor and reactive components, it again develops the drop across resistor and reactance as I2R2 and I2X2 respectively. And hence we can find out the terminal voltage by connecting a voltmeter across the load. So this is the diagram of actual transformer. So it's an equivalent circuit. And then what happens to the phasor diagrams? For that, we have to keep in mind that we are dealing with primary winding resistance and inductive reactance. Similarly, secondary winding resistance and inductive reactance. So these two we have to keep in our mind when we are dealing with the actual transformer. So what we know about the R load phasor diagram: R load without windings in the primary with uh, resistance and reactive components. This is the phasor diagram which we have already obtained. Now we will try to obtain the actual drops included in the transformer primary and secondary. For that, you can see we have a flux, we have the induced voltage E minus E1, E2, which are opposite to each other. Then the new voltage equation you can see here, E2 is equal to V2 plus I2 Z2, where Z2 is replaced by R2 plus JX2, and I2 is the current which is flowing through this particular impedance parameter. So this is the voltage equation. In order to satisfy this voltage equation from the phasor diagram, you can see I2 we have selected in this fashion, and V2 and I2 are taken as in phase. So these two are in phase because we're talking about the resistive load. Okay. Then the load component of the primary current is treated as I1 dash, and we know that the no load current is also taken as I0. With these two, active component and the magnetizing component uh, of the transformer gives the primary current, that is I1, in this fashion. This we already seen from the previous load conditions. So now we have I2R2. So I2R2 is a drop which is in phase with I2. So that is why I have taken a line from A to B and I have marked it as I2R2. Then I2X2 is a perpendicular, that is the inductive component acting perpendicular to this resistance drop. And with these two combinations, I'll get the impedance, that is I2Z2, which will be a arrow mark which is subtended from A to C. For easy understanding, I have not shown over here, but you can assume that we have to connect another vector from A towards C, and that vector is nothing but I2 Z2. Fine. So this gives us the value as E2, which is shown already here as E2 is equal to V2 plus I2 Z2. Now, opposite to minus E1, we have E1 and E2, which is already assumed to be in phase. Now, from D dash or minus E1, we are taking a line parallel to I1, and the drop is treated as I1 R1, and that line is defined as D dash F. Now, this is parallel to I1. Now, I'll be projecting from F towards G, the perpendicular, that is the drop across the reactance, that is I1 X1, and these two components, as I told you, will be resulting in I1 Z1. So this is the vector which is obtained because of these two vectors. Now finally we have V1, which is given by minus E1 plus I1 Z1, or in fact V1 is equal to minus E1 plus I1 R1 plus J X1. So this is a phasor representation of actual transformer with primary resistor and inductive reactance, as well as secondary resistance and inductive reactance. So the angle between the I1 and V1 is phi 1. So this already we have seen from actual diagram also. You can see here you have phi 1, which is between I1 and V1. So that is a change of this actual phasor diagram with the previous phasor diagram. The another illustration you can see, I have taken the load component of the power factor and treat it as phi 2 dash. So in order to understand the concept in detail, I have elaborated in each and every step in these statements. You can read those statements neatly and you can prepare notes according to these statements for your convenience or for your understanding. And that is how we have framed the equations of V1 and V2. Now what happens if we take the inductive load? The equations remains the same, but the phasor diagrams according to this load, it will change in this fashion. You can see again I have taken 0 and 5, and I have taken current and voltage because of the inductive nature of the load. You can see the current lags voltage. Current is the blue line and V2 is the green line. So these two are the voltage condition and current conditions of inductive load. Now we know that I2 and I1 dash is the load component of the primary current. With this I0, I can frame the value of I1 as we have already seen from the past class. And as I told you, I have to take I2 R2 drop, which is acting parallel to I2 in this fashion, and perpendicular to this I2 X2 is traveling like this. And with this I'll get I2 Z2, which is shown by this light blue line. Now this leads to the value of E2, which is given by V2 plus I2 Z2. Right. Now pertaining to E2, we have minus E1 in this fashion, and I1 gives the value of a drop across primary resistance, which is acting parallel to this line in this fashion, and perpendicular to this line I have I1 X1 as the reactive component, and with these two vectors I'll get another vector as I1 Z1, and with this I'll get the value of V1, which is nothing but equal to minus E1 plus I1 Z1. The same analysis we can do for capacitance. So for the capacitance also, you can see the diagrams are projected in this fashion. So this is a phasor representation, and that is how we obtain the value of V1. What is the conclusion of these three cases? Whether it is inductive load, capacitive load, or resistive load, the phasor diagrams, they get changed based upon the voltage and current conditions. So that's all for today's class. I hope you like this particular session. Please subscribe to this channel and share the video among your friends. Thank you.